Alright, boys and girls, welcome to our second video lesson in Chapter 3. Our lesson on logarithmic functions, the inverse of exponential functions. Alrighty, here we go. Okay, as we just said, logarithmic functions are the inverse of exponential functions. So if f of x is an exponential function, if f of x equals b to the x, then the inverse of f is log base b x. In other words, this exponent right here, the x, becomes our log, and the y is the function itself, okay? And we'll go through this in class. So, logarithmic functions are the inverse of the exponential functions. So let's just graph right now in red your basic exponential function. Our intercept, our critical point is 0, 1. There it is. It's asymptotic on the left, and it shoots up to the right, getting big quickly. And again, our domain is all real numbers in an exponential function. And our range is just the positives. Y has got to be greater than 0, but not equal to 0, because it's asymptotic. Okay, the logarithmic function now is going to be the reflection over the line y equals x. So our critical point goes from 0, 1 to 1, 0. We have an x-intercept at 1. It's asymptotic on the lower side. It's asymptotic to the y-axis on the negative side, and it shoots off to the right very quickly, but it continues always going up. So if we talk about the domain of a logarithmic function, it's like the range of an exponential function. X has got to be greater than 0. It cannot equal 0 because we're asymptotic here on the y-axis. And the range is all real numbers. Okay? Notice that our logarithmic function is asymptotic for the total negative values of y, and it shoots off to the right on the positive y's, but it does continue to go up forever. Okay, the restrictions on b are just like before. Just like before, our restrictions on b is b cannot be 0, 1, or a neg. Our restrictions on x is that x must be positive because our domain we know is positive. And y, of course, can be all reals because our range is all reals. Okay? The transformations for a logarithmic function are just like they always have been. Okay? Our a represents our vertical stretch or compression. So as our a becomes a number, it stretches it out. A large number, as a becomes a fraction, it squishes it. If a is negative, it's going to flip it over the y-axis. It's going to turn the graph upside down. If our b is a fraction, then it reflects over the x-axis. Okay, if b is a fraction, it reflects over the x-axis. And again, notice that b cannot be neg. Our h is our horizontal shift, and our h is also our vertical asymptote. Okay, it's our vertical asymptote, and our k, just like before, is our vertical shift, and our critical point, which is typically at 1, 0, will always be the point h plus a, k if you are a mesmerizer. All right. So 2 more words you need to know. A common log is a log of base 10. That's important in math because we do work in the decimal system. So a common log is a log of base 10. We often, if you see a log without a base, we assume that to be a common log base 10. The natural log is log of base e, also very important in math because we use e for exponential growth, for continuous exponential growth. We write a natural log with ln as opposed to log. Log natural. Lago natural. Okay. Alright, you guys take a moment here, match these graphs up. I did the best I could. I know it's hard to see, but I think you can figure out which graph is which. Take a moment, stop the tape, and match up these graphs. Okay, our first two are our basic logarithmic functions, so that would be either b or d because they go through the x-intercept of 1 comma 0. D shoots off to the right faster than b, so d would be the log base 10, and b would be log base e, which we know is 2.78ish. Okay, not quite as big as 10, so our second one is b. It does not shoot off to the right as fast as d. Graph number 3 is the exact same thing as D, but it moves 3 places to the left. So notice that our asymptote in C is at -3, so this is C. 4 is the exact same graph as B as well, but this time, as D, but it shoots up. It moves up 3 places, so that would be A. And 5 is upside down, and it goes down 2 places, so it is E. Okay, a couple properties of logs that are important to you. These are our basic properties. Number 1, log base b1 is always 0, and that is because b to the 0 power is 1. Don't forget, when you take a log, this means b to the 0 power is 1. Okay, log base b is always 1, and that's because b to the first is b. So b to the first is b. Log base b to the x is b to the x. Is x, because b to the x is equal to b to the x. And the last one is our other inverse properties of logs. Log base b to the log bx is equal to x, and these two again are called our inverse props of logs. And our logarithmic property of equality says if log base bx is equal to log base by, then x is equal to y, and that's because if b to the x is equal to b to the y, then x is equal to y. Okay, let's figure out these. Log base 2, 8 is equal to what? So we got to ask ourselves, 2 to what power is 8? We know that 2 to the third is 8, so this is equal to 3. If I say log base 2, 32 is equal to what? We say 2 to what power is 32? We know that 2 to the fifth is 32, so this is 5. Okay, if I just look at this next one, 2 to what power is 256? We know that that is 8 because 2 to the 8th is 256. You guys stop the tape for a minute, see if you can figure out the rest of these. Again, so our answers are here. The first one is 3 because 2 to the third power is 8. The second one is 5 because 2 to the fifth is 32. Our next one is 8 because 2 to the 8th is 256. Our next one is 5, and you can see now it's important to memorize your powers. 3 to the 5th is 243. Number 5, or the fifth one, 3 to the second is 9, so the answer is 2. Now these are a little bit trickier. You must remember that 9 to the 1/2 power means the square root of 9. So 9 to the 1/2 power is 3. So the next one is 1/2. The next one is 4 because 10 to the fourth is 10,000. The next one you can see now the property of the inverse property. 10 to the fourth power is equal to 10 to the fourth. So this answer is 4. The next one, our inverse property again, is 8 because 2 to what power is 8? Well, it's third, so 2 to the third is 8. Okay, and I know those are confusing. It's almost so simple it's hard, but that answer is 8. 2 to what power is 1/4, 0.25. Well, that would be 2 to the -2. 3 to the 0 power is 1. So log base 3, 1 is always 0, or log base b1 is always 0, no matter the base. And the last one is -8 because if 2 to the 8th is 256, the reciprocal of 2 is 1/2. So we got to take the reciprocal power. So 1/2 to the -8 is 256. Okay, one of your homework problems, some of your homework problems, it asks you to write this in logarithmic form. So we're going to do that right now. So this means that 9 to the 3 halves is 27, which means log base 9 27 is equal to 3 halves. Notice that the log is always equal to the exponent. Okay, this is our answer. This is our base. 9 to the 3 halves power is equal to 27. Let's do a couple of graphs and then we'll be done. In this particular case, what is our A? Well, our A is 1. There's nothing in front of the log. What is our B? Our base is 10. Our H is -2. And our K, there's nothing outside here, so that is 0. We just talk about your basic logarithmic graph. I'll do this in purple still. It's asymptotic at the lower y-axis. Goes through the point 0, 1, and then it shoots off to the right. It does continue to go up forever, but it goes up very, very slowly. And this shoots off to the right relatively quick because our base is 10. Well, the h of -2, all it does is it just moves our entire graph 2 places to the left. So our new critical point is at 0, -1. The asymptote is -2, and then it shoots off to the right, just like before. So there is our graph in blue. All right, let's look at this last one. Our A is still 1. There's a 1 right there in front of the log. Our B is still 10. That means it's going to shoot off to the right relatively quickly. Our H in this case is 2. You can see that 2 right there. And also, if I wanted to, I can move my 1 to the end. I don't have to, but my K is 1. I could think of that as +1 at the end. So if I ignored my H and K, I would have a critical point right here at 1, 0. It's asymptotic on the lower y-axis. It shoots off to the right relatively quickly because my base is 10. But now what happens to my critical point, we'll do this in blue. My critical point is going to go right 2 and up 1. So my new asymptote is at x equals 2, so it shoots down and is asymptotic here. And then it's also going to shoot off to the right and get big relatively slowly off there to the right. All right, folks, I think that's it. Have a great day. We'll see you soon. Bye.